Welcome to Lecture 11 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we're going to start our work on the theory of the firm. In particular, today we're going to focus on what's called short-run production. Before we do this, we need to find out what we mean by a firm in microeconomic theory and what we mean by the short run and the long run. So let's get started. If we recall when we started our work on consumer theory, we summarised a consumer's intentions with a very basic idea. Now, of course, people have lots of intentions in real life, but our consumer had only one goal, which was to choose the most preferred affordable bundle of goods. Similarly with firms in real life, there may be many objectives that firms have, but we're going to make this simple and state that in our models, firms are entities that exist to do only one thing, and that is to maximize profits. So the firm's objective is simply to maximize profits. Now, in order to do this, we will typically model a firm choosing the appropriate level of output to produce. So they're going to be choosing a quantity, an amount of a good to produce, which they will then sell to the market. When deciding how to produce, we're going to discuss the idea of efficient production and minimizing cost. There may be many ways in which you could produce the same amount of a given good using different combinations of different inputs, more machines, less people, or more people and less machinery, and so on. So we'll talk about what we mean by producing efficiently and minimizing costs towards the end of the course. The profit maximizing output decision can be formulated mathematically as the following. We're maximizing profit by choosing an output Q. Profit is typically denoted with the Greek letter pi. So we're maximizing pi by choosing Q, and profit is essentially equal to revenue minus cost. Well, this is an identity. Profit is identical to the money that you make, your revenue, minus how much it costs you to produce that level of output. Okay, and when we say CQ, we call this the cost function. And this is the minimum cost of producing Q. Okay, you could always spend more simply by burning money, for instance. We will assume the firm doesn't do this and that they choose a cost minimizing way of producing this output. We'll talk a lot more about that. So when we're talking about maximizing profits, there are two parts to this, the revenue side and the cost of production side. Now, revenue is going to be mostly determined by what we could call the market structure. This is really the topic of semester 2, so we won't go into it, but let me give you a brief introduction to how revenue is determined by market structure and how we might model different market structures. So revenue is, of course, the money that you make by selling your goods. So revenue is the price that you get for your goods multiplied by the quantity of goods that you can sell. How is this price determined? That's what we mean by a market structure. So different market structures determine this price in different ways. If revenue as a function of Q is simply equal to P times Q, where P is a constant unit price, then we call that a competitive market. Why does this make sense? Well, the idea of a competitive market is that there are many firms and each individual firm is very small in comparison to the whole market. Because of this, no single firm has the power to affect this price level. So, however it is determined, it is essentially treated as a constant. The market, in some sense, chooses this price level P, which everybody accepts. This is called price-taking behavior. And in a competitive market, we take this price level and multiply it by how much we are selling to get our revenue. Now suppose that a firm does have what we call market power. So price is a function of the firm's output Q. and only of that firm's output Q. So here I've written revenue Q is the price as a function of the firm's output multiplied by the firm's output. Given that this firm has the power to affect the market price and that they're the only firm who is affecting this market price, this is what we mean by a monopoly market. If the market price were affected by other firms, for instance, on the next line I've written an example, your revenue of producing Q1, so firm 1's revenue, is determined by, well, the price of good 1 in that market is determined by the output of firm 1 and the output of firm 2, being multiplied by the output of firm 1 in order to get the revenue. This is what we would call a corno-duopoly. So the price is being determined by two firms' output decisions, and these output decisions are made independently. An alternative model of duopoly is the Stackelberg duopoly. In this case, the market price, P, is a function of the output of firm 1 and of the output of firm 2, but the output of firm 2 also depends on the output of firm 1. So you can imagine, in some sense, firm 1 going first and choosing their output, and then firm 2 choosing their output whilst knowing what firm 1 has done. So these are not independent choices. There is a sequence of moves in this case. So that's what we call a Stackelberg duopoly. There are two firms, and the first firm goes first, and the second firm chooses their output, knowing the first firm's decision. If we had N firms in the market and the price is being determined by the output of firm 1 and firm 2 all the way up to firm N, and these firms are acting independently, well, we call this a corno-oligopoly. Okay, so there are many more examples, and essentially to model different market structures, you are making different assumptions about that price being determined by quantity, which we called inverse demand. So different inverse demand functions, depending on different inputs in different ways, is the precise way in which you can model many different market structures within the basic framework of profit maximization. The cost of production, which we've denoted C of Q, depends on the firm's technology and the prices of inputs. So we'll be very precise about what we mean by this, and over the next 4 lectures, lectures 11, 12, 13 and 14, we're going to study both production in the short run and the long run, and costs in the short run and the long run. So that's our objective towards the end of the semester. And in semester 2, you'll be looking at applying these ideas in different market structures. In today's lecture, we're going to be looking at short-run production. So what do we mean? How do we model production in microeconomics? Well, the idea is that a firm uses inputs, or sometimes called factors of production, which they combine in using some production technology to produce outputs, which is a good. So they're going to use different inputs using some technology to produce an output, which can then be sold. We formalize this relationship mathematically using what's called a long-run production function. Now, in general, there could be many factors of production, but for simplicity and for drawing diagrams over the next few lectures, we're going to just imagine the firm uses 2 different factors of production: labour, which will denote capital L, and capital, which will denote capital K. So labour you could think of as the amount of hours of labour being employed by the firm, and capital is, in some sense, the machinery, the infrastructure, the buildings, warehouses, and so on. And these come together to produce an amount of output Q. So the long-run production function, which we'll denote by F, is as follows. Output Q is a function, the long-run production function F, when we plug in a certain amount of labour and a certain amount of capital. So for different levels of labour and different levels of capital, you get possibly different levels of output. Of course, given specific values for labour and capital, the firm could always produce less than this specific amount Q simply by throwing some output away. So the production function, we must remember, describes the efficient amount of production for each combination of inputs. It's the amount of production, the maximum amount of production that is possible using them inputs with no waste. Today's lecture will focus on what we call the short run. Now, in microeconomics, the long run and short run have specific definitions. In particular, short run and long run are not defined as explicit time periods. Okay, so when we say short run, we don't mean this week, and long run meaning 15 years. We mean something much more specific than that, but without mentioning the explicit time period. So this is the definition. In the long run, all factors of production are variable. So in our model, where we're having labour and capital, if a firm is able to produce output and choose different quantities of labour to employ and different amounts of capital to employ, then that is what we call a long-run decision. Okay, so in the long run, the firm is able to reorganize its production by changing both the labour it employs and the capital it employs. In the short run, at least one factor of production is fixed. Okay, so for us, we will mean exactly one factor of production is fixed. But if there were many factors of production, n factors of production, for example, then if at least one of those is fixed, if the firm cannot change every input, if it has to accept a certain level of at least one input, then we're talking about the short run. Okay, so in the short run, you could imagine that there is simply not enough time to change all the inputs. So for instance, if a firm was running a factory, it has a certain amount of machines, then in the short run, day to day, perhaps the firm can vary the amount of labour hours it employs. But replacing the machines, moving premises, building a larger factory are what we would think of as long-run decisions. So changing both labour and capital would be the long run. And if capital, for example, seems more natural, if capital is fixed, then changing the amount of labour that is employed day to day would be considered a short-run decision for us. As we're talking about the short-run production today, we're going to fix capital at some level, capital K bar, which is greater than 0. We could have chosen to fix labour and varied capital. It's completely arbitrary, but it seems natural to fix capital just to fit with our story about machines and premises and allow the employment of labour to be the variable in the short run. So we'll fix capital at K bar, in which case, now we can take the long-run production function is something that the firm is assumed to know. The firm is aware of their technology. They know how much they can produce with different quantities of labour and capital. So using that long-run production function, we can derive a short-run production function. Q is equal to, and then F of L, with K fixed at K bar. So really this is just a function of L, and we're taking capital K as a parameter rather than a variable. So this diagram here shows a kind of typical case. It's at 0 when we employ 0 units of labour, there is 0 output. Here this is often called labour is an essential input in this particular example. It's not always the case that inputs are essential, but we typically assume it for labour. So it starts at 0, and here we have an increasing and concave function. We'll see more specifically what that means throughout this lecture. Now, using this short-run production function, there are several concepts that will be of great use as we proceed. The first is the idea of the marginal product of labour. Now, let's define this in words, in maths, and diagrammatically. Okay, that's what we typically want to do when defining ideas in economics: words, maths, and pictures. So in words, the marginal product of labour is essentially the additional input the additional output produced when we employ an additional unit of labour. So if I have 10 units of labour and I employ an 11th, by how much does my output go up or go down? That's what we call the marginal product of labour. Now, mathematically, we're going to think of labour as a perfectly divisible quantity. So you could think of as labour measured in time, for example. We're going to imagine this being perfectly divisible and a production function being smooth. So we can take a derivative and say the marginal product of labour is the derivative of the short-run production function with respect to its input labour. Okay? So that would be a mathematical definition. And we know that a derivative like this in a diagram, if we're evaluating the marginal product of labour at a specific point, here I've labelled a point L, then I would look at the production function at L and then draw a line that is tangent to the production function. And the slope of that line would tell me the marginal product of labour at that particular point. The next important idea is called the average product of labour. Okay, so average product of labour is defined exactly as it sounds. We say, well, if we're employing L units of labour and our output is F of L, then on average, how much is each unit of labour producing? Well, we take that F of L and divide it by L, and we call that the average product of labour. Okay, so on average, how much is each unit of labour producing? Mathematically, it's F of L divided by L. Graphically, in order to see this average product on a diagram, essentially what we would do is we would connect the short-run production function evaluated at L and then draw a line from that point back to the origin. So here I've drawn a pink line which connects the 0 up to F evaluated at point L. And in this case, if we look at the slope of this pink line, well, this is essentially rise divided by tread. So this is how you would measure the slope of this pink line. Turns out to read off exactly the average product of labour. So let's go on to paper and we'll work through a very commonly used example of a production function known as the Cobb-Douglas production function. So let's have a look at a well-known example of a long-run production function and a short-run production function called the Cobb-Douglas. You may recall this from utility theory as well. So it's a very similar functional form. So Cobb-Douglas long-run production function. And the form it takes is output is equal to some constant A multiplied by how much labour the firm uses to the power alpha multiplied by how much capital the firm employs to the power beta. Okay, so this is the Cobb-Douglas long-run production function where we're assuming that this constant A is strictly positive, and we're going to assume that alpha is strictly positive and beta is strictly positive as well. Okay? So this is the Cobb-Douglas long-run production function, where I'm thinking of it as a function of two variables, L and K. Now, for us, we're going to look at the short-run production function. So if, let's say, K is just equal to K bar, so if K is just fixed at some K bar, then the short-run production function we could write as Q is equal to, then we'd have the A times K bar to the power beta. So let's just denote that, just to be consistent with the notes, I used gamma times L to the power alpha, where gamma is just our constant parameters, A, K bar to the power beta. Okay, so this would be the short-run production function. that arises from the long-run Cobb-Douglas production function when we take capital as fixed at some value k bar. Okay? So perhaps we could produce a diagram of this. Now I'm going to assume that alpha is between 0 and 1. Okay? Now in general that does not need to be the case. In fact, we will interpret alpha and beta in lecture 13 when we discuss the idea of homogeneity and returns to scale. But let's imagine that alpha is between 0 and 1 for now. Certainly we imagine it's greater than 0, but let's suppose it's less than 1 as well. Okay, so what would be the marginal product of labour in this case? So what I would do, I would differentiate my short-run production function with respect to labour. And we know how to do that. I would get alpha times gamma L to the power alpha minus 1. Okay? And of course, this is, it's always positive. Okay, so every term here is positive. So overall, this is positive for all values of L. So what does that tell us? If the marginal product of labour is always positive, it tells us that our short-run production function is always increasing. Okay, if the marginal product of labour were negative, I would have a decreasing part of this short-run production function, which is fine in general, but it doesn't happen in this case. Okay. What about the average product of labour? So the average product of labour in this case, how would we find that? We would take Q and divide it by L. Okay. Or alternatively, we would take gamma times L to the power alpha and divide it by L. In which case, we would get gamma times L to the power alpha minus 1. Okay. So in this case, we would get that the average product of labour here, it looks like the marginal product of labour, except it's missing this alpha term here. And I've assumed alpha is less than 1. So here the marginal product of labour is equal to the average product of labour multiplied by something that is smaller than 1, greater than 0. So here marginal product of labour will always be below the average product of labour. Okay, that's going to be, we'll find an easy way to interpret that towards the end of the lecture. But let's just do this mathematically for now. What else can I say about this marginal product of labour? Well, let's differentiate it again. So if I differentiate marginal product of labour with respect to L, okay. So this is the second derivative. I'm differentiating twice the short-run production function with respect to L. Okay. So what would this be? I would have alpha times alpha minus 1 multiplied by gamma L to the alpha minus 2. Okay. Now this term, and this term are positive, but this term in the bracket here, alpha minus 1, is negative. So the second derivative here of the short-run production function is negative. Its first derivative was positive. So what does that tell us? Well, we know that means that this short-run production function is an increasing but concave function. We know that if L is 0, then Q is 0. So we've kind of gleaned enough facts to draw a reasonable diagram. It starts at 0, it's increasing, but it's concave, okay? So something like that would be our short-run production function. What about these marginal? Well, I know that the marginal product of labour is decreasing because it's the derivative of the marginal product of labour with respect to L is negative. So this is a decreasing. So it's going to start very high, and then as L goes to infinity, this is going to tend to 0. So it's going to have this shape like this. So this would be the marginal product of labour. What about the average product of labour? Well, mathematically, I can see that the marginal product of labour is the same as the average product of labour, but just multiplied by something that is smaller than 1, greater than 0. Okay, so average product of labor is just going to be above marginal product of labor everywhere. So something like this just captures the idea of what's going on in this diagram. Okay. Now, there's a nice thing to notice here, which we'll come back to towards the end, that if I look at every point here, if I pick a particular L, then the marginal product is below the average. Okay. Now, what does that mean? Let's interpret that in economic terms. It means if I employ another unit, okay, so if I employ somebody else, the marginal product is going to be below the average. Now, if you think in terms of your grades, if you get one more grade and it's below your average, you know that your average comes down, okay? So if I employ one more person and that person is producing less than the average, then the average is being pulled down. So the fact that this average product of labor schedule here is downward sloping, decreasing, is related definitely to the fact that the marginal product of labor is always less than the average. So every time we employ another unit of labor, it's pulling that average down. The short-run production function, the Cobb-Douglas function that we've just studied on paper, the way we derived it with this alpha less than 1, we drew an increasing and concave short-run production function. This type of production function exhibits an economic property that's called the law of diminishing marginal returns. Like the law of demand, this is not something that we always expect to hold, but it's a general idea, so it's worth knowing about it and pointing out where this property is exhibited by a short-run production function. The idea of the law of diminishing marginal returns is that with each unit of labor we employ, although they are increasing our output at a decreasing rate. Okay, so the increment that each unit of labor adds to our output diminishes as we employ more and more. So that generates a concave production function. Even though it's increasing, in this case it's concave as well, which means the first derivative is positive, it's increasing, and the second derivative is negative. This characterizes diminishing marginal returns, and you could use this idea for any particular factor of production by partially differentiating with respect to that factor, holding other factors constant. And if we see a negative second derivative, then we see diminishing marginal returns. The classic case that you will often see in textbooks is not the case of law of diminishing marginal returns holding everywhere. Typically, you'll see diagrams where for small values of labor, we observe this initially convex part of a short-run production function, so increasing marginal returns. For small values of labor, each unit we employ is adding an increasing amount of output. And then this is followed by diminishing marginal returns eventually. This seems to fit various cases. For example, if we think about a simple agricultural example, if a farmer, for instance, owned 3 fields and 2 tractors, well, if he employed 1 unit of labor, then that one person could perhaps drive 1 tractor and get through 1 field. If there were 2 units of labor, perhaps we could have 2 fields being done, and then help working together, they could do a bit more, and a third helping even more, and so on. Eventually, this process, as we employ more and more people, perhaps they begin to get in each other's way. So each person, though helping and increasing output, is doing so at a diminishing rate eventually. So this is kind of an old story that seems to fit the agricultural type of example. In the textbook, a short-run production function, which is a cubic function, seems to exhibit these properties. So let's have a look at this in more detail a short-run production function of the type Q is equal to labour L plus 30L squared minus L cubed. If we were given a short-run production function like this, could we produce a set of diagrams, one of the short-run production function itself, one of the marginal product of labour, and one of the average product of labour? Okay. Doing this exercise is sometimes called producing a set of short-run production schedules. So producing a set of diagrams that show the short-run production function itself, the average product of labour, and the marginal product of labour in diagrams relating the relevant values to each other. So let's jump on paper and do this now. Okay, so for this exercise, we've been given a short-run production function, f of L is equal to L plus 30L squared minus L cubed. Okay, and our task here is to produce a diagram of the short-run production function, of the marginal product of labour, and of the average product of labour. Okay, so the first thing I'll do, I'm going to use some tricks from calculus to help me produce a nice set of diagrams. I don't need to be incredibly accurate because it's just a sketch, and you'll see what I mean in a minute by that. But we're going to do our best, so that our first job is really to kind of gather as many facts as we can. And then when I've gathered these facts, I'll be able to produce some nice diagrams. So first of all, let's find the marginal product of labour. Okay, so the marginal product of labour would be the first derivative of this with respect to labour, which is quite simple. It would be 1 plus 60L minus 3L squared. Okay, so that would be the marginal product of labour, the first derivative of the short-run production function with respect to labour. The average product of labour would be the short-run production function f of L and then divide it by L. Okay, so if I do this here, L divided by L is 1. 30L squared divided by L is simply 30L. And minus L cubed divided by L is simply minus L squared. Okay, so I have the mathematical expressions. At this point, I could use some graphing software and just put these values in. But we're going to use calculus to kind of find out as much as we can about this. And I'll kind of keep a list over here of the things that we know. So the first thing that's going to help us here as well, if I plugged 0 in, so let's just make a note that f of 0 equals 0. Okay, so labour is an essential good here. When does this marginal product of labour equal 0? Okay, so marginal product of labour equal to 0 occurs when 1 plus 60L minus 3L squared equals 0. Okay, so this is a quadratic equation. There's going to be two solutions in this case. So if we were to use the quadratic formula, let's just remind ourselves if this is the A, this is the B, and this is the C, then you could use the quadratic formula and say, well, this is 0 when L is equal to, and it would be minus the B term, so minus 60 plus or minus the square root of b squared, 3600, minus 4ac, so we've got minus times a minus, so plus 4 times 3 times 1, so plus 12. Let's extend that square root, all divided by 2a, which is minus 6. Okay, so that's the precise, if we remember from GCSE mathematics, I guess, this would be the two solutions to this. The plus and the minus will give you the values of L that make MPL equal to 0. I'm going to just do a trick here and say, well, look, the square root of 3600, I can do that in my head. That's 60. And this plus 12 is much smaller. So this is approximately equal to minus 60 plus or minus 60. Okay, so this is approximately 60. It's not exactly, but it's approximately divided by minus 6. In which case I know that L is, well, it's approximately 0. That would be the minus 60 plus 60. Or L is approximately 20. Okay, so there, it's not exactly 20 where MPL is 0, but it's roundabout. It's good enough for a diagram. Okay, so we'll put on our list of facts over here, MPL is 0 when L is approximately 0 or when L is approximately 20. Maybe we could make a note as well that F, if we evaluate F at 20, if you just take 20 and plug it in here, 20 plus 60 times 20 squared minus 20 cubed, I've done in advance, I got 4,020. But double check my numbers, okay? Now this would be, because this is where MPL equals 0, this is the maximum of F. Okay, so the derivative of 0, it's either a minimum or a maximum or an inflection point. But I won't verify, but I know in this case that this is actually the maximum amount of output. So employing 20 units of labour produces 4,020 units of output. If I keep employing more beyond that point, my output will start going down. If I employ less, my output will be lower. Okay, so this is the maximum possible level of output for this short-run production function. So what else can we say about this? What about learning a bit more about this marginal product of labour? Perhaps we could find where this is maximised. So if I take the derivative of this marginal product of labour with respect to labour, okay, I'm differentiating this expression here. I simply get 60 minus 60L, okay? So I know that MPL max is where this derivative is 0. So at L is equal to 10 in this case. Okay, so let's make a note over here. MPL is maximized. What does that mean? It means, well, it's the highest point on the MPL curve, and it's also the steepest point on the short-run production function. So where this function is steepest, where MPL is maximized, is at L equals 10. Okay? And you could just calculate that at that point, F of 10 is equal to, if you plug 10 back into this, you'll get a value I did in advance of 2010. Okay. What else can we learn about this? So we know the marginal product of labour. We know it's a minus quadratic, so it's a concave curve. The minus quadratics have this frowny face look to them. I know that it's maximized where L equals 10. I know that it crosses the horizontal axis, so it's 0 when L is approximately 0 or approximately 20. So I kind of know enough about the marginal product of labour in itself now. Let's have a look at average product of labour. So for instance, when is this 0? This 1 plus 30L minus L squared. Now, if I do the same trick as I did up here, LPL is 0 when, and if I just do it approximately, so, and I can kind of read this, I say, well, if 30 times L squared and 30L will be equal to each other when L is about 30. Okay, so there'll be a 1, but that's close enough to 0 for us. So this is 0 when L is approximately 0 or L is approximately 30. Okay, not precisely, but approximately. So APL is 0 when L is approximately 0 or L is approximately 30. Okay. what about this where does the maximum APL occur? So if I differentiate APL with respect to L, I take the derivative of this, I would get 30L minus 2L, okay? From which I can see, well, if L was equal to 15, apologies, not 30L, 30 minus 2L, then if APL is 15, APL is max at L equals 15. Okay, so APL max when L is 15. Okay, I could calculate F of 15. I got 3,390. Okay, I'm not sure if all of this will be useful. I'm just gathering as many facts as I can. So the highest point on this APL curve, it's a negative quadratic. It starts at 0. It crosses the axis. Well, it starts approximately at 0. It crosses the axis approximately at 30. Its highest point is L equals 15. We could calculate the APL at that point as well if we wanted. Now let's compare this MPL and APL. What can we say about this? Well, what if they were, where do they cross each other, or do they cross each other at all? Because we're going to draw them on the same diagram. So if I solve this equation, MPL equals APL, so I'm solving the equation 1 plus 60L minus 3L squared is equal to 1 plus 30L minus L squared. Okay, this looks more complicated than this is. An awful lot's going to, the ones will cancel out straight away. I can divide by these L's and get rid of these. So I get a nice simple expression that this occurs when L is 15. Okay, so you can double check that. I encourage you to do that. So MPL equals APL at L equals 15, which is also where APL is maximized. So where this curve reaches, this APL curve reaches its highest point is where it's going to intersect this MPL curve. Okay, so we've very quickly just made a list of relevant, hopefully relevant points about these. So now when I actually come to produce a diagram, so I'm just going to cover up all of, I've made notes here. I'm going to cover these up and produce a diagram. So I know, for instance, let's have a look at the marginal product of labour. It starts at about 0. L equals 10, 15, 30 seem to be relevant. So let's put these on the diagram. Let's put 10 here, and 15 here, and 20 here. We'll leave 30 off. I think it was left off in the textbook as well. So the marginal product of labour is going to start at 0. It reaches its highest point when labour is equal to 10. Okay, so somewhere here. And then it's 0, MPL equals 0 when L is approximately 20. Okay, so if I just take these into account now and just draw something that kind of captures those basic ideas and then comes down to 20. Okay, and then is negative afterwards. So this here is a reasonably accurate drawing of the MPL curve. I could, if I wanted, take the kind of calculate this value at the top here. I'd just be plugging in 10 into this equation, 1 plus 60 times 10 minus 3 times 10 squared. I think I have written that down somewhere, so that would be 301. Okay. So that's the marginal product of labour. What about the average product of labour? It's also a negative quadratic, so it's going to have the similar shape. What did we say? It's approximately 0. It's 0 when L is approximately 0, so we're going to draw it's kind of starting in the same place. It's maximised where L equals 15. Okay. And also we know at 15, it crosses this MPL curve. Okay, so it's at 15, it's going to be equal to the marginal product of labor curve, and it's going to be increasing up to that point and decreasing afterwards. So let's see if we can draw this reasonably well. Okay, so that's the general negative quadratic shape, starts at 0, crosses the marginal product of labor curve, where APL attains its highest value. Okay, and then decreases after that. Okay, so we can actually see an idea. We'll prove this formally, but we can see here that when the when the marginal is above the average, it's pulling the average up. In the same way that if your next grade is higher than your average, your overall average goes up. That continues until they just touch. And then when the marginal product of labor is below the average product of labor, each extra unit we employ is producing less than the average, so it starts pulling that average down. Okay, so this fact that MPL equals APL, where APL is maximized, has a very nice, easy intuition, which you can just think about your next grade and your average grade to get the basic idea. Okay, so we've got these. Now let's try and draw the short-run production function. We've said it's going to be... let's just trace some relevant points from this diagram. So it's going to start at 0. What else do we know? That it's steepest at... so MPL is maximized at 10. So this is where this production function is steepest. And where is APL maximized? At 15. Okay, now if we remember APL, it was if we draw a straight line. So let's just kind of plot that one point and then go from there. So if I was to connect these two with a straight line, okay, not sure if that comes out on camera, but I've just connected this point with a straight line back to the origin, and the slope of this line is the marginal product of labor. As the average product of labor, at 15. And I'm saying that's at 15, APL is at its highest value. So the short-run production function has to stay below this line at all. If I extend this line, it's always going to be below this line and just touch this line here. Okay, it's at its steepest value at this 10, and at 20. What do I know? Marginal product of labor is 0. So that's where it's maximized. Okay, so at this point 20, it's going to be the highest point. So let's try and draw something that captures this idea. It's starting from 0, it's getting steeper and steeper and steeper until it reaches 10. That's its steepest point. Then it becomes less steep. Then it just touches there. It's maximized and then starts coming down. Okay, so this would be our short-run production function. Okay, so hopefully you can see the idea. It's a rather basic exercise. We're just using the definitions of marginal product of labor and average product of labor. And then we're just throwing in calculus here and there to find out, well, where's the highest value on this curve? Where's the highest value on this curve? Solving the equations to find where these curves intersect. Finding out as much information as we can, and then bringing it all together to produce a reasonably accurate diagram. I could label these points. Back on the axis was 40, 20. This point here was 3,390, and so on. So once I've got these values, I may as well include them on the diagram and label them specifically. Yeah, so that's the basic idea. Find as many facts as you can, throw every trick from calculus at it that you can, and then in doing so, you'll be able to produce kind of the very best simple sketch in only a couple of minutes of these types of diagrams. So one point that I've mentioned when we were deriving our short-run production function for the cubic case was that it just turned out that the average product of labour and the marginal product of labour coincided where average product of labour was maximised. And we had a nice intuitive story for this. Now, one question you might ask, because if the intuition was convincing, it might be something we'd like to prove more formally. And also, it's something that, is it specific for the function that we drew? Is it only true for cubic functions, or is it true more generally? So this is what we're going to prove now. So what we're going to prove is that MPL is equal to APL, where when APL is maximized. Okay, so how could we prove something like this? So the first thing we'll need, just to recap, now I expect you've seen this before, but it's worth just mentioning once to be certain about this, is the quotient rule from calculus. So this rule says something along the lines of if I have a function f of x, and it's the quotient of two functions. So if it's equal to g of x divided by h of x for all x. Okay, so if I have a function which can be written as the quotient of two functions, then if I want to differentiate f with respect to x, there's a specific formula for doing this. So I differentiate the g function. So I differentiate g with respect to x and then multiply that by h. And then I deduct g multiplied by the derivative of h with respect to x. And then I take all of this and I divide it by h squared. Okay, so this is something I expect that you've seen. It's similar to the product rule, which you should also revise, but with this little extra, the minus sign, and then the dividing by minus h squared is the little twist for the quotients. So let's apply this now. We know that APL, the average product of labour, is equal to the short-run production function f of L divided by L. Okay, so we could think of these as two functions. The one on the top is f of L, and the function on the bottom is just where I plug in L and out pops L. So it's just the identity function. So if I differentiate this, if I differentiate APL with respect to L, okay, let's use this quotient rule. I'm going to differentiate the top, or what did I call that? The marginal product of labour, and then multiply it by L. So that's the first expression here. Then I'm going to deduct the derivative f of L. This is our g. And then differentiate the bottom, which of course is just dl. So that's just equal to 1. Okay. And then I divide everything by L squared. Okay. So if I tidy this up a little, I'm going to take one of the L's outside the bracket. Okay. And then what have I got? Marginal product of labour multiplied by L divided by L once. So I just get marginal product of labour. And then minus f of L divided by L here. Okay, which is of course 1 over L, the marginal product of labour, minus the average product of labour. Okay, so this is the first derivative of the average product of labour function. And you can see that if, to maximise the average product of labour, I'm choosing the L that makes this derivative 0. So essentially when this bracket is equal to 0, that's when APL is maximised. And of course this is equal to 0 when MPL is precisely equal to APL. Okay, so that's a mathematical proof of the idea that average product of labour is equal to marginal product of labour when average product of labour is maximised. The intuition again was very simple, that when marginal product of labour is below average product of labour, it's pulling the average down, And when it's above average product of labour, it's pulling the average up. So when they intersect is where APL goes from being pulled up to start being pulled down, which is, of course, the maximum. Okay, but this is the formal proof, which is the nice thing about looking at these things analytically. The intuition may have been nice, but this is a formal proof, which is absolutely convincing. So that concludes our work on short-run production, the short-run production function and the short-run production schedules, marginal product of labour and average product of labour. It was a rather simple lecture today, just based on being able to produce informative diagrams when you're working with a parametric short-run production function. In the next lecture, we'll be looking at the long-run production case, where both capital and labour can vary at the same time. This will require more sophisticated tools. Similar to indifference curves, we'll be developing the idea of isoquants, looking at marginal rates of substitution in factor space rather than commodity space, and setting ourselves up to study the long-run cost minimization problem in the final lecture of this course. So lots of interesting things to come, and I look forward to seeing you next time. In the meantime, take care.